So first let me say that this is a talk for people who don't already know Apache Arrow. So if you already know or use it every day, I hope you will learn something new. Otherwise, you're free to blame me. So let's get started. I'm Alessandro, and over the course of the year, I've been maintainer and author of a few open source projects related to Python. And recently, I became an Apache Arrow contributor, and my job is as a director of engineering at Volton Data Labs. And Volton Data takes care of helping with maintenance of Apache Arrow and some of the core projects that are based on top of Apache Arrow. And I'm also the author of the Modern Python Standard Library Cookbook and the Crafting Test-Driven Software with Python books. And today I'm here to introduce you to Apache Arrow. The first question is, what's Apache Arrow? And that's an interesting question because it's many different things. Apache Arrow was born as a data interchange standard and in memory format. So it was a way to represent data for data engineering, data analytics, for software like NumPy, Pandas, and those kind of software. They needed to cooperate and interact. Arrow was a format they could use to collaborate together over the same data without paying the cost of converting it between each one of them. Then it also became a format to transmit that data across the network and a format to store that data on the disk and a library to load multiple different formats that are common to store data for data science like Parquet or ORC or CSV files. Arrow started to implement effective and fast loaders for all those formats into the Apache Arrow format so that those libraries could easily load data from those formats into the Apache Arrow one. Then it evolved into a tabular data library because obviously when you load data, you need a way to represent it in memory and make it accessible for your users, your developers. So it evolved into a full tabular library. Then it grew a query engine to be able to perform computation on top of that tabular data. Then it grew a way to support partitioned data, so it became also the partitioned datasets manager. So it became a lot of things over the course of the years, and it's continuing to evolve. There is a lot inside Arrow, and the reason is that the mission of the Apache Arrow is to give you a world where you can write software once in any language you want, you like Go, Python, Ruby, whatever, and they all have a available implementation of Apache Arrow, so you don't have to learn anything new. And you can collaborate with people that use other languages. So you might write a piece of software in Go and another piece of the same software in Python, and they will be able to collaborate over the same exact data in memory because the data is represented in the Arrow format in both cases. And then you will be able to run the analysis that you have everywhere on different kinds of hardware transparently to you because Apache Arrow supports inside the compute engine multiple different architectures, CPUs, and it's also optimized for remote execution through Substrate, which is a query interchange format, I would say. So PyArrow is the entry point to the Arrow world for Python developers. And that's what I'm here to talk to you about. And obviously, Arrow was born as a columnar data format because that's the most frequent way you will represent your data when you're going to perform data analytics. So the foundation of Arrow is a column of data. A column of data is represented in Arrow as a PyArrow array, and it has many subclasses for specific types of data. But at this level, you can think of PyArrow as something very, very similar to NumPy, even though it's less powerful from the point of view of operations you can apply to this data, because Arrow wasn't really meant wasn't born as a tool for data scientists. It was born as a tool for software engineers that need to write their own algorithms on top of that data. And here you can see a simple example. We'll tell you why I told you that it's similar to NumPy, because in practice you have a PyArrow array, and you can represent multiple different kinds of data into PyArrow, including structured data, and obviously it supports natively mask for arrays, differently from NumPy. And the interesting part is not all the kind of data that it supports, I would say, because that's something that you already have available in other tools. But the fact that the underlying memory format is heavily optimized for this data. So the underlying implementation of PyArrow is written all natively in C++ and assembly. So even though you are writing Python, you are in practice using a proxy to the C++ memory. That's, for example, if you know how NumPy internally works, NumPy is a continuous buffer of data, but it doesn't have a concept, for example, of null values in the sense of actual null values. If you want to represent a null value, you just put a none into the data. But instead in PyArrow, you have every array has a validity bitmap, so it's already stored to account for null values, and it's also heavily optimized for strings. If you ever worked with strings in NumPy, you probably know that it's one of the major bottlenecks, because in the end it uses Python strings, and that doesn't make it very fast or effective or memory efficient to store string data, text data in NumPy. While PyArrow uses a dedicated string representation format, which in practice stores the string as a single continuous buffer. So you have multiple strings in an array, you have multiple words or text or whatever in a single array, and they are not stored as separate strings. They are stored as one single huge string. Why this is effective? It's effective because it allows you to apply SIMD extractions very efficiently on top of your data when you are doing to scan through it or perform operations or things like that. So what I'm trying to tell you is that Arrow is maybe not as effective for a data scientist, but it's heavily optimized for people who need to write tools for data scientists. So the typical Arrow developer, user, is someone who is writing a database system, someone who is writing a compute engine, or someone who is writing a library to load data from disk. Those kind of developers are usually those that benefit a lot from Arrow. And as obviously we are talking about columnar data, that means that we probably are interested in having more than one column, and that's why PyArrow evolved also to provide the tables. And tables are stored by chunked array. Why chunk array? Because one of the major costs when modifying tables is usually when you append data, you have to reallocate the existing columns to extend them. While by using chunk arrays, the appending data to an Arrow table is in practice a zero cost operation depending on where the data comes from, I would say. At this level, the PyArrow table is something very similar to pandas data frames, I would say, okay? So here, for example, you can see a PyArrow table. It's a very simple table with some number of strings and columns. Obviously, you can build it through many different syntax. So, for example, you can use a dictionary instead of a list of arrays with names and things like that. But it was just to show you the raw idea of what I'm talking about. And why do we care? Because over the data that we have, we can obviously perform many different operations. In the case of Arrow, it provides built-in a compute engine which is named Arrow, which is optimized for various architectures at the moment, but it Given that Arrow is a data interchange format, it supports also many different compute engines. For example, Velox from Meta is one of the engines that supports Arrow and is able to directly execute analytics on top of the Arrow data. Or QDF is growing support for Arrow. Actually, it has support for Arrow. So once you have your data in the Arrow format, you can really combine the pieces as you wish, depending on what's best for your use case. Those are examples of the built-in Apache Arrow compute engine. So for example, you see that I made a table, I filter it for all the rows that are equal to a specific value, and then I run a simple aggregation, a group by, and then I join two tables. All these operations are implemented into the C++ compute engine. So they are usually far faster than what you might be used with pandas or equivalent tools. We are going to see it in a minute. But the main reason why Arrow is very interesting and important is the one that I was telling you about it being a lingua franca for data interoperability between different software. So for example, in the past, if you had your data in Parquet or Cassandra and you wanted to analyze it from pandas, you have to copy that data, which was in a dedicated format in Parquet, was in a dedicated format in Cassandra, and you have to convert data from that format in whatever pandas format used in memory, and you also had to pay a cost of unmarshalling that data and storing it into a different format in memory. While given that all those tools are slowly embracing PyArrow, Arrow itself more than PyArrow, now it's possible to move data across all different software without paying any marshalling and unmarshalling cost. And for example, Spark now supports Arrow natively. So if you want to perform a pandas data frame operation on top of data that you have in Spark, that's something that you can do for free because they will use the same exact data. You won't pay any cost of shipping the data from Spark into pandas and vice versa. And the overall reason why Arrow has grown into its own set of capabilities, it's because by leveraging the knowledge about the internal representation of the data, given that the developers of Arrow know very well how the data is represented, they could implement very effective and efficient operations on top of that data. So for example, here you can see the comparison between finding all the unique values into an array. And in one case, I'm running NumPy unique, which will tell me the unique values and how frequently they appear into the data. And in the second example, I'm using PyArrow value count over a PyArrow array, which does the same exact thing. So it tells you which are the unique values and what's their frequency. And you can see that in case of NumPy in this system, it took more than a second, while in the case of Arrow, it took 300 milliseconds. So that's why I was telling you that it was very fast. And by very fast, I mean that, for example, now pandas uses Arrow itself. You can use Arrow itself as the underlying engine to load data in pandas. And for example, if we compare the time that it took when using the built-in data loader for pandas and the time that it takes to load the same data in Arrow and then convert it to pandas. So we are not just loading the data. We are loading it and making a pandas data frame out of it. So in practice, we are doing two different operations. And doing those two different operations is faster than just directly loading the data into pandas itself. So usually it's better for you if you go through Arrow and then convert to a pandas data frame. That usually ends up being faster. And for example, I was telling you that the Pandas itself now supports Arrow as an engine. So if I read a CSV file using the built-in Pandas reader, it takes 13 seconds, while if I use the PyArrow engine, so I pass the engine equal PyArrow to the Pandas reader, it takes only 3 seconds. So it's far faster loading the same exact data in the same exact library. So you still get a Pandas data frame out of it from the same exact CSV files. So you get a 3-4 pair bonus for free in practice. And why my talk is titled as a full stack solution? Because as I told you, Arrow has been growing over the course of the years, and it has grown from an in-memory format to one that is able also to store data on disk. Then it grows its own compute engine, then it grows its network format. And why this is important? Because they are all heavily integrated together. And the fact that they are heavily integrated together means that I can benefit from a huge speed up because I have no marshalling and unmarshalling cost in all these chain. For example, if I read a Parquet file, so Parquet is its own format, it's not PyArrow, it is optimized for loading in Arrow, but it's not the Arrow format, on disk format. I took just some random data, and that takes 2 seconds in this case to load in Arrow, so into a PyArrow table. And if I store that same data into the Arrow on disk format instead of using Parquet, you can see that the same exact data, instead of taking 2 seconds, takes 2 milliseconds. So this is important because it allows you to store your data in a way that it's effective for direct usage of that data. So while we might want to consider Parquet something like a cold storage for data that you need to frequently access, that you are working on right now, what you might be called your working set, you might want to store it in Arrow disk format itself because it will be hundreds of times faster to load it back. Not only it will be far faster, but if you notice, I explicitly use the memory map function here. And that's because by memory mapping the file, I'm not constrained by my computer memory anymore. I can load an amount of data that is bigger than my memory, and the kernel will automatically swap in and swap out the pages for you without you having to care for doing that yourself. This means that if I have a Parquet dataset which is bigger than my memory, I won't be able to load it in my memory because it will be bigger and it has to be fully decoded into memory. While if I use the Arrow disk format, I can only load these pieces that I need at that specific moment and then offload them back to the disk itself when I don't use them anymore. Which is usually the case for data analytics because you don't look at the whole array, at the whole column at the same time. You usually scan through it. So you, in practice, only care about the specific piece where you are running your operation at the moment. Obviously, it would be great if we could use the Arrow disk format every single moment, but by virtue of the fact that it has to represent exactly the memory format, it's far bigger than using something like Parquet. That's why I say that it's probably good to have Parquet as a cold storage solution, while Arrow only for the hot data, for the working set. And if you think about that, the reason is pretty obvious. It's that we could not implement any compression format into the Arrow disk format. Well, you can, but if you implement the compressed format, it becomes, at that point, it's slower, a lot slower to load back the data because it's no more a direct mapping of that data to disk. It needs to decompress it, it needs to convert it, and things like that. So that's why usually for Arrow data, you keep it uncompressed, so it will be as big as that data is actually. While for something like Parquet, you will compress it, and also Parquet supports dictionary encoding and a whole set of optimization for disk storage. So the lesson that we get is that it's actually possible to read a big data set in just a matter of milliseconds if we use the right tool. So whenever you are facing something that is a bit slow, you might want to look if Arrow provides the same capability for you, because it will probably allow you to do the same exact thing that you were doing in Pandas or in NumPy with frequently no code change at all, because you can convert to Pandas or NumPy format, and you will just get a huge speed boost for free. Then I told you that Arrow is been evolving also to a network format, and the name of the technology that implements network support in Arrow is named Flight. So we have Arrow Flight, and it's built into PyArrow itself. So if you want to expose your data over a network between two or more processes or software that need to collaborate and ship data between each other, Flight is something that solves that exact problem. And I won't get too much into the details of how Flight works, but you might want to know that it's being inside Arrow world itself, it's heavily optimized. The same concept that we have seen for the disk applies to the network. In practice, Flight is built on top of gRPC, but it has no marshalling cost. So it does not convert the data to gRPC. The data is shipped exactly as it is. So if you imagine you have a file on disk with your data and you need to ship it to a software on the other side of the network, you can directly take the data from the disk and copy it on the network card buffer without having any single CPU cycle involved in the middle, because it's the same exact data moved from one buffer to the other. And Flight is explicitly designed to allow you for that. So for example, for the coordination, for the RPC and those kind of commands, it will involve gRPC, the standard gRPC protocol. But whenever it needs to ship data, it will hijack into gRPC, bypassing the whole format and just writing the raw buffer to the network. On the other side, you receive the data already in the format you want, because it's already in the Arrow format, and you just copy it into the memory without any marshalling cost. Why this is interesting? This is the reason, because suppose that you have data in a database, and that database could support both Flight and ODBC, which is the most frequent standard that you're probably going to use to assess a database. And reading 5 million rows or 1 billion records into ODBC, it's going to take a lot of time, because you have to convert between the formats that your database has on disk, your database ships on network, your driver or ODBC driver wants. And if we use Flight for the same exact operation, loading that data from the database into your software, it's going to take like orders of magnitude less. So we are comparing seconds, thousands of seconds to 1 to 3 seconds or something like that. So it's a huge speed up. And that's why I think that Flight can actually make your data fly. It can make it very, very fast. And Arrow is evolving even further, so it's no longer constrained to the capability that we have seen. I told you that it now has built-in, and it actually had for years support for Parquet, so you can natively store data in your Parquet files, and Arrow will seamlessly load them without any additional library or operation involved. Then once you have your data into the memory, you can share it with any other software using NanoArrow. NanoArrow is in practice a super small version of Arrow whose only purpose is to allow any other software to implement the Arrow format without having to manually operate on top of the memory buffers. Okay, so it's an API on top of the raw memory. And it's like very easy to use in any software. The reason why it was born is because it's one single header file. You just copy it in your application if you are a C developer, and that's it. You don't have to care about dependencies. You don't have to care about building an object file. You just copy that header file, you include it, and that's done. You have full support for accessing Arrow data. And these allowed people to implement more advanced capabilities on top of Arrow, like ADBC and Flight SQL. Flight SQL is in practice a standard to ship SQL queries and data on top of the network using Arrow. So databases that are going to implement Flight SQL are going to give you data directly in the Arrow format. And ADBC is a database driver optimized for Arrow, so for columnar data. If you think about it, now the majority of the database drivers have a huge problem we're working with data science, which is that they were originally designed to work with raw major data. Usually when you load something from the database, you care about your user row, your article row, and things like that. So the drivers are optimized to reason in that direction. While ADBC was designed to work on columnar data, so it actually allows very effectively to load the data already in the Arrow format and in column major representation. One interesting fact of Flight SQL is that it's not only very fast because it allows marshalling, but compared to most formats to access data on databases, it also provides parallel data access. So it means that if you have to load 3 columns, it's not going to load them sequentially from a single database connection. It's going to parallelize the loading of the columns through 3 different connections. And given that it's underlying implemented in C++, it will use real threads, not Python threads. So you will actually benefit from the fact that it's parallelized when loading that data from the database. And Flight SQL is convenient because it allows you in practice to leverage the Arrow speed while using standard code that just uses the Flight client and things like that. ADBC instead needs you to write your code specifically for ADBC, so you will have to go to the ADBC library. The database will have to support ADBC drivers and things like that. And the good part is that the core developer of ADBC is doing a lot of that for you. So at the moment, it already supports PostgreSQL, and DuckDB. They are all supported natively by ADBC, and it's growing support for more database and technologies over the course of time. And if you are interested, I think it's very cool that inside the ADBC repository itself, there is a super simple implementation of ADBC for SQLite. So like it's few lines of code, you can look at it and in like an afternoon you will know how to implement your own driver for whatever database you care about. And I told you also that we are slowly working to integrating another very cool technology in the Arrow system, which is named Substrate. So if you think of Arrow as the lingua franca for data, so the golden standard for interchange of data, Substrate is the equivalent for queries. So instead of shipping text, SQL, and things like that, you will have a heavily optimized binary format to represent queries and send them across different software, which will all talk Substrate. And the interesting part is that Substrate is implemented for slicing of those queries. What it means? It means that if you have a very complex query, imagine that you have a, I don't know, a join with a filter over the two tables that you are joining, okay? And imagine that you are executing that query given the Substrate it's a format for distribution across different technologies that all understand Substrate. You might be loading one table from one database and one table from a totally different place, a Parquet file, for example, using Arrow. Arrow understands Substrate and it supports loading data from Parquet, so you might be performing a single query that joins a Parquet file to Arrow to a table on Postgre. And what the Substrate technology will allow you to do is to take only the piece of the query that is related to the filter and forward it to the technology behind your client. So for example, the filter part will be submitted to Arrow, which will filter the data before sending it to the engine that will perform the join itself. So suppose you have three different things. You are using Velox, and Velox has to read data from a Arrow dataset and from a Postgre file. The Postgre database will perform the filter. The Arrow compute engine will perform the filter. They will send to Arrow the already filtered data, and then Arrow will perform, to Velox in my example, and then Velox will only perform the join. So you are integrating three different technologies and offloading every piece of your query to each one of them. And one of the very cool ideas is that those queries could be pushed down to the hardware itself. For example, suppose that you have a smart disk, you could push the filter for the partition keys to the disk itself. So the disk could only load the files that are actually involved in your queries, instead of having to scan through them and see which one contains the data that you care about and things like that. So it's a technology that will be very flexible and powerful in the future and will allow us to go in the direction of write your software once, test it on your local machine, and then deploy it into a huge cluster without changing a single line of code, because they all understand Substrate, they all understand Arrow, and they speak the same exact language, and they guarantee to provide you the same exact results without changing a single line of code. So for example, here there is a quick example of ADBC. And why I put it here, why it's interesting, because in the first case, I obviously load the data into Arrow, obviously, like ADBC is the Arrow driver, so you expect to be able to load the data into the Arrow format. But by virtue of the fact that Pandas supports Arrow natively, in the second case, I'm running a query on top of SQLite and getting back the results of that query into a Pandas data frame. And that's all for free. Like, there is no conversion cost or things like that. The ADBC driver gets the data into the Arrow format, and Pandas understands the Arrow format, so it's able to create a data frame on top of that data for free. So that's a good example of why I'm telling you that Arrow allows you to seamlessly integrate many different libraries and technologies. And over the course of the years, given that it's a very interesting technology, that it's allowing data science to evolve in many different directions, it has been growing very quickly. You can see that the amounts of downloads is it's growing exponentially, and in this year we reached the 7 million monthly downloads. So if you want to try Arrow, you can just go on the PyArrow documentation, which is on the arrow.apache.org docs/Python. Or you can look at the PyArrow cookbook. The cookbook is a very cool documentation piece which will provide you ready-made snippets for the most common operations. So frequently, if you need to do something, you just open the cookbook, look for the recipe that you care about, and use it. It's like Stack Overflow for Arrow, but there are, of course, a lot of questions on Stack Overflow too. So, and if you have any question?
Sorry, just very quick request. Thank you for an excellent presentation. I've not used Arrows before, but I'll start looking at it tonight or tomorrow morning. One request though, because it takes a while for the videos to go up for the conference. Could you put your slides up somewhere, please?
Yeah, absolutely.
Yeah, if you have on LinkedIn or something, that'd be great, please. Thanks.
No worries.
Thank you very much. That's a great presentation. I just kind of wanted to clarify a little bit. So when you showed us the different kind of technologies that are can be used from memory to database to disk, there was a whole kind of ecosystem of different. It wasn't this slide; it was the other one. Was the kind of like the data going between different systems? This one. So it's just kind of hard for me to kind of picture it, but are you saying that every single of those would use exactly the same format? There is no need for conversion?
Yeah.
Because I would imagine that for legacy reasons, maybe memory could be a little bit different from how the disk was structured in the most optimum way. And same for databases. It's the underlying technologies.
That's a good question in the sense that there will be some cases where the underlying technology will provide a optimized conversion. We should distinguish between two cases. One is a technology that is fully Arrow from end to end. So for example, if we take DuckDB, that's a fully Arrow database. So it's able to give you data in Arrow format without any form of conversion cost at all. But if we take, for example, Parquet has to convert the data because it's obviously, it must unmarshal the data from the Parquet format. So even though the Parquet library now provides a very effective and optimized decoder specifically designed and built for Arrow, so it can benefit from some optimization based on the fact that it already knows that it's going to decode things into Arrow format. For example, for some kinds of data, it does not have to decode anything at all because the buffer, the way that Arrow represents the data in memory might be the same exact way that Parquet is storing the data into a row group. So there might be cases where we can benefit by optimization, but obviously in a case of a technology like Parquet or Postgre, they will have a optimized decoder, but still a decoding phase in place.
Okay, thank you.
Cool. Anyone else?
Here.
Hi, thank you very much. It's very helpful, and especially I have many use cases in my workplace. I do read a very large CSV on a daily basis through my automation, and so my question is, because I don't have data on my machine, it's on the servers, shared servers, and and I don't know which Pandas version supports the engine where we can use the Arrow. So my question is it a good start where I can just try to read using the engine PyArrow, and if that needs any prerequisites of any version, Pandas version, and
if your Pandas version support the PyArrow engine, it will obviously work. Otherwise, it will give you an error, and otherwise you could just use PyArrow for loading the data and then invoke the toPandas function to convert it into Pandas and then continue with Pandas from there on. And also the PyArrow library supports access to many different storages. So for example, you could have your data on S3 or places like that, and PyArrow itself has built-in support for those. So you don't have to download the data locally and then load it from disk or things like that. For example, in the case of S3, it will benefit from chunk transfer and parallel transfer of the different chunks and things like that. So you might want to try with just Pandas if you already have a code base passing the engine equal PyArrow. And if that does not work, you want to just use PyArrow, load data to pandas, and continue like before.
Thank you. And I just have one more stupid question. In terms of visualizations, there are many libraries that support the data frame where I can just throw my data frames into the, for example, Plotly, and we can get the...
Sorry, can you raise your voice a little bit?
Sorry. No, my question is around the visualizations.
Yeah.
There's a support.
Oh, yeah.
Is there any support, or can I use Plotly with...
At the moment, the support for visualization library is very limited, but one thing that it's going to come with the upcoming version of PyArrow, the one that should release at the end of the year, maybe January, but like that, is support for the data frame interchange protocol, so which is a Python standard format to access data frame-like data in whatever classes or objects is stored. And any library that supports that protocol, which is many libraries out there, will be able to access a PyArrow table as it was natively supported. Obviously, it won't be as fast as if it had native support for PyArrow table, but at least you will be able to use it. Otherwise, as I told you, the solution, the hack, is always to just call two pandas and use whatever library supports pandas. As I shown before, the cost of converting to pandas is like non-existent because they use 90% of the time the same exact memory layout. Actually, in the recent version of pandas, I fairly sure that it uses PyArrow itself for string columns. So instead of using NumPy, which uses for the other columns, it uses PyArrow in case your column is for string type.
Awesome. Thank you.
You're welcome.
Maybe one more question, if anyone has one. Now we can finish up and say thank you very much, Alessandro.
Thank you.
Fantastic stuff. Thank you.